After studying this module, you shall be able to know about anomalous magnetic moment for various transition metal complexes, learn about some examples of the octahedral, square planar and tetrahedral complexes of nickel 2 plus, iron 2 plus or cobalt 2 plus showing anomalous magnetic moment. Identify various factors responsible for anomalous magnetic moment. Evaluate the equilibrium between two spin states for some nickel 2 plus, iron 2 plus, iron 3 plus and cobalt 2 plus complexes.
Introduction. Anomalous magnetic moment is the magnetic moment for a metal ion in a discrete molecular species having a value which falls outside the range of values predicted from considerations of the spin and orbital angular momentum in ligand fields of given strength and symmetry. The discrete molecular species means that there is no secondary magnetic interaction between the neighboring molecules. In other words, for these systems, there is not any ferromagnetic or antiferromagnetic interactions. It explains these systems are magnetically dilute. Let us briefly understand the meaning of anomalous by taking some examples. Octahedral complexes, nickel 2 plus complexes. For nickel 2 plus, in a regular octahedral geometry, the 382G ground state term nickel 2 plus acquire some orbital contribution from the next higher 3T to G state term due to spin orbit coupling. The overall magnetic moment is dependent on delta value and lambda. Assuming delta is equals to 8000 centimeter inverse and lambda is equals to 75% of the free ion value, mu effective can be calculated by using the equation. The value of alpha is 2 for Eg ground state term and 4 for an A2G ground state term. The calculated mu effective is about 3.3 Bohr magneton, which is fairly above the spin only magnetic moment of 2.83. This also includes a small temperature independent paramagnetism contribution. Generally, mu effective is in the range from 3 to 3.3 Bohr magneton, although noticeable value in excess of this have been noted. The metal ions Fe2 plus, Fe3 plus and cobalt 2 plus also show the similar considerations. However, in some instances, orbital angular momentum for the ground states of these ions in firm octahedral symmetry are not quenched and the expression for mu effective is more complicated. For these cases, there also exists the possibility of high spin and low spin complexes with variations in the ligand field. For the high spin octahedral cases of Fe2 plus, Fe3 plus and cobalt 2 plus, there is a rather complicated dependence on lambda and Kt iron 2 plus complexes. For iron 2 plus, the free ion term is 5D state and the absence of adjacent higher terms of the same multiplicity simplifies calculations. The ground state in octahedral symmetry is 5T 2G and mu effective is expected to have a value of 5.6 Bohr magneton at room temperature. Experimentally, movements of 5.1 to 5.7 Bohr magneton are observed. Fe3 plus in weak ligand fields has a 6A1 ground state coming from a free ion 6s state, and movements of the order of 5.9 Bohr magneton are generally found. Cobalt 2 plus complexes. For octahedral cobalt 2 plus high spin complexes, the ground state configuration is T1G, resulting from a free ion F ground state. Two cases are considered for the calculation of mu effective. First, the ligand field is small compared with the interelectronic interactions. Second, the field is large compared with interelectronic interactions. The calculated mu effective is in the range 4.7 to 5.1 Bohr magneton. Values found experimentally fall in the range 4.7 to 5.2 Bohr magneton, depending on the ligand field strength and the amount of distortion from octahedral symmetry. Tetrahedral complexes relatively large contributions to observed movements from orbital angular momentum are expected and observed. For regular tetrahedral complexes, mu effective should occur within the interval 3.5 to 4 Bohr magneton. Tetrahedral cobalt 2 plus complexes usually exhibit movements closer to the spin only value, and these are of the order 4.2 to 4.4 Bohr magneton. Tetrahedral Fe2 plus and Fe3 plus complexes are somewhat rare. Square planar complexes. Square planar nickel 2 plus complexes have no unpaired electron and exhibit essentially zero movements or small contribution due to temperature independent paramagnetism. Square planar cobalt 2 species are, however, paramagnetic and are reported to exhibit movements in the range 2.1 to 2.9 Bohr magneton, having slightly larger orbital contribution than low spin octahedral complexes. The normal and anomalous magnetic moment for nickel 2 plus, Fe2 plus, Fe3 plus and cobalt 2 plus complexes are summarized here in table. From this table, we can see that the range of anomalous magnetic moment for the nickel 2 plus complexes is 0 to 2.8 Bohr magneton. For cobalt 2 plus complexes, it is 2.9 to 4.2 Bohr magneton. For iron 2 plus, it is 0 to 5.1 Bohr magneton, and for Fe3 plus, it is 2.3 to 5.9 Bohr magneton. Factors responsible for anomalous magnetic movement. A variety of models has been proposed to account for the anomalous magnetic moments of different metal complexes. These may be discussed under the following categories. First is equilibrium between two spin states. Second, magnetically non-equivalent sites in the unit cell. Third, solute-solvent interaction. Fourth, solute-solute interaction. Fifth, configurational equilibrium. Now let us briefly understand these models by taking appropriate examples. Equilibrium between two spin states. As we know that the ligand field causes splitting of the 5 degenerate d levels of a transition metal ion into two or more separate sets of levels, depending on the symmetry of the field. For fields of octahedral symmetry, two such levels, higher energy Eg set and lower energy T2G set are produced. For weak ligand fields, the spin multiplicity will be the maximum obtainable for any given number of d electrons in accordance with Hund's rule. For strong fields, on the other hand, for which the energy separation delta of the Eg and T2G set of the orbitals exceed the electron pairing energy, the more stable configuration for D4, D5, D6 and D7 systems will be one in which the T2G level is completely filled before any occupation of the higher energy Eg level occurs. Thus, hexaamino iron 2 plus exhibits a magnetic moment of 5.45 Bohr magneton, which is a high spin complex, indicating the presence of 4 unpaired electrons, whereas hexacyano iron 2 plus complex is diamagnetic, which is a low spin complex. For nickel 2 plus complexes of octahedral symmetry, there is clearly only one way in which the 8d electrons can be arranged for states of lowest energy. All regular octahedral complexes of nickel 2 plus must therefore show a paramagnetism corresponding to the presence of two unpaired spins. The situation changes, however, whenever an axial distortion is applied to the originally regular octahedral field. Such distortion lowers the symmetry from octahedral to D4H and is accompanied by a further loss of degeneracy of the d orbitals. When this tetragonal distortion is large, the energy separation between the dx square y square and dz square orbitals delta 1 or between dx square y square and dxy orbitals delta 2 may exceed the electron pairing energy. In this case, there will be a change in magnetic moment from 3 Bohr magneton to 0. Conceptually, tetragonal distortion can be envisaged as arising by moving the two ligands on the z-axis to greater distances from the metal ion. In fact, this occurs only for certain electronic configurations and is an example of Jahn-Taylor distortion. Alternatively, and more subject to control, the absence at these axial positions of different ligands which exercise a different perturbation on the d orbitals from those in the xy plane will generate the effect. In high spin nickel 2 plus complexes, only the later type of tetragonal distortion is found, as in mixed complexes of type nickel A4B2. The figure represents the change in orbital energy levels as the symmetry is progressively lowered from that of a regular octahedron to a strong tetragonal structure. It is clear that tetragonal distortion leads in the limit to square planarity and a coordination number of 4 proceeding in the reverse direction for a square planar complex nickel A4 which interacts along the z-axis with two ligands B, there will be a reduction in energy separation delta 1 or delta 2 of the two highest energy orbitals. For weak interactions, such as would be caused by ligands low in spectrochemical series, for example, iodide, delta 2 may still exceed the pairing energy. On the other hand, if the separation of the ligands A and B in the spectrochemical series is relatively small, then delta 2 may be less than the pairing energy and a change in spin multiplicity will occur. Even in this simple model, it is necessary to remain aware of the dependence of the pairing energy on the nature of the donor atoms. For a fixed value of delta, reduction in magnitude of the pairing energy may produce the low spin state. There are many examples of series of tetragonal nickel 2 plus complexes wherein a relatively small change in nature of the axial ligand brings about the predicted magnetic crossover. For example, a series of NN prime diethyl ethylene diamine complexes fall in two categories: diamagnetic and paramagnetic, with mu effective is equals to 3.1 to 3.33 Bohr magneton, and the crossover in ground states occurs between X is equals to Br diamagnetic, X is equals to Cl with mu effective is equals to 3.29 Bohr magneton. The sharpness of the changeover is demonstrated by the fact that chloride and bromide occupy adjacent positions in the spectrochemical series. Similar results have been observed for planar nickel 2 plus complexes with quadridentate ligand shown here. Here also the magnetic moment varies with the nature of the axially coordinated univalent groups. Thus, the perchlorate and iodide are diamagnetic while the bromide in CHCl3 solution, chloride and thiocyanate are paramagnetic. Certain systems are explicable on the basis of equilibrium between coexisting singlet and triplet states, whose energy states differ by amounts comparable with thermal energies. For such equilibrium between spin isomers, the distribution between the two states can be described by Maxwell-Boltzmann statistics. If it is assumed that there is no change in structure other than the alteration in spin state, it has been shown that the magnetic susceptibility is given by the equation shown on the screen, where G is the Lande splitting factor, N is Avogadro's number, beta is the Bohr magneton, K is the Boltzmann constant, T is the absolute temperature, delta E is the energy separation between the singlet and triplet states, and N alpha is the temperature independent paramagnetism. The factor 1 by 3 arises because a small increase in entropy is associated with the increase in spin multiplicity. Other sources of entropy change are ignored. It follows from this equation that the magnetic susceptibility will increase with temperature except where delta is much lower than kT. It explains when the singlet and triplet states are essentially degenerate. This is of course the opposite direction of change for chi A from the predicted by Curie-West law. The nickel 2 plus complex of NN prime diethyl thiourea is spin paired at temperature 194 Kelvin but attains partial paramagnetism at the temperature is raised. The corresponding bromide and iodide are diamagnetic at room temperature, but the bromide becomes slightly paramagnetic at 373 Kelvin. The relative abundances of the triplet states among the three halides is that predicted by the Mackey and Balhausen and Leher treatment of nickel 2 plus in D4H symmetry, since the separation between the singlet and triplet states is least for the chloride, which lies closest in ligand field strength to the substituted thiourea. It is believed that nickel 2 plus has a weak tetragonal field, and the magnetic property is dictated only by the thermal population of two spin states. For the equilibrium singlet to triplet state, the equilibrium constant K is given by K is equals to concentration of triplet state divided by concentration of singlet state. K can be calculated from the knowledge of the mole fraction gamma Hs and gamma Ls. The relation between chi m and mole fractions is shown here. Now this relation can be converted in the terms of magnetic moment and mole fraction and is given by, now the equilibrium constant is found out to be equals to mu square experimental minus mu ls square divided by mu hs square minus mu square experimental. The gamma Hs and gamma Ls can be calculated at different temperatures by using the given equations. The gamma Hs, gamma Ls, mu effective and K for the given complex at different temperatures are shown here in the table. The data suggests that effective magnetic moment and equilibrium constant K is increasing with temperature. That means low spin complex is converted into high spin at higher temperatures. This suggests that the magnetic crossover is the main cause for anomalous magnetic moment of this complex. The spin state alteration causes the decrease in metal donor distance when the triplet states changes into the singlet. Another interesting example of nickel 2 plus showing spin state isomerism are found among the complexes with planar quadridentate macrocyclic ligands. A series of 6 coordinate tetragonal complexes have been synthesized by changing the singly charged anion X. The table shown on the screen summarizes the data obtained for these systems. The anhydrous perchlorate, tetrafluoroborate, and tetraphenyl borate salts of the complex are diamagnetic, whereas its anhydrous thiocyanate, nitrate, and iodide are paramagnetic. The monohydrate, chloride, and bromide salts of the complex exhibit anomalous room temperature magnetic moments. These values suggest the spin state equilibrium in chloride and bromide salts of complex. Noting that the chloride and bromide form surprisingly stable hydrates, they assumed that this hydrate water takes part in the equilibrium. It has been demonstrated that the order of crystal field strength in the halide salt is anomalous. The water molecule may form strong hydrogen bond with the singlet chloride or bromide salt, but not with triplet chloride or bromide salt. This is because the residual charge on halide is maximum for singlet state, since the nickel halide bond is weak in this state. Thus, the contribution of the hydrate water to the energy balance system is very crucial. If the anomalous magnetic moment arises from a fixed mixture of two spin states, then a linear Curie-Weiss plot will be obtained for S1 state. But if spin state equilibrium is temperature dependent, the composition of the mixture will change with a change in temperature, and Curie-Weiss plot will be non-linear. The increasing deviation from linearity in Curie-Weiss plot at higher temperatures is attributed to spin state equilibrium between triplet ground state and low-lying singlet excited state. Thus, from the nature of Curie-Weiss plot, it is possible to distinguish between first, a fixed mixture of two spin states, second, spin state equilibrium between two spin states. In an octahedral crystal field, the spin state equilibrium is possible for configurations showing on the screen. Around crossover region in each of these configurations, the energy of the two spin states differ by kT, so that the relative populations of the two spin states vary with temperature. The D5 and D6 configurations have spin orbit coupling integrals Ls between the two terms of differing spin multiplicities as 0, so that there is no significant spin orbit interaction between two spin states. The overall magnetic susceptibility of each of these configurations may be taken as population weighted average of the magnetic susceptibilities of the two terms as shown on the screen, where S1 and S2 are spin quantum numbers, chi m1, chi m2 are molar susceptibility of two spin states, delta is equals to E high spin minus E low spin is the energy difference between the two spin states. For D4 and D7 configurations, the spin orbit coupling integrals between the two spin terms as non-zero. Consequently, magnetic susceptibility equation becomes extremely complicated. Iron 2 plus complexes. An interesting spin state equilibrium has been observed in the iron 2 plus complex of ligand 2-pyridyl amino 4-2-pyridyl thiazole, cobalt 2 plus and nickel 2 plus complexes of the same ligand have been found to be spin free. However, for iron 2 plus, there is a strong dependence on the ion and in some cases the degree of hydration. The chloride salt of the complex has two spin isomers. One is yellow, showing normal high spin behavior, and other is red-brown, predominantly spin paired. In all cases, a sample which has high moment at room temperature appears yellow, and as the temperature is decreased, it becomes red-brown. For D6 configuration, S1 is equals to 0, S2 is equals to 2, chi m1 is equals to 0. So we can put these values. The equation reduces to delta is equals to kT ln 5 chi m2 minus chi m divided by chi m. The delta values of the complex at various temperatures obtained vary as much as 400%. Except for the bromide complex, the plots of log K against T are not straight lines over the whole temperature range, but may show continuous curvature or have segments with approximate to straight lines of different slopes. Such deviations indicate something besides vertical spin state equilibrium and may be attributed in part to a modification of the crystal lattice. Iron 3 plus complexes. The prime example of spin state equilibria involving iron 3 plus occur with NN dialkyl dithiocarbamates. There exist three types of behavior depending on alkyl substituent. Room temperature movement range from high spin to minimum value of mu effective is equals to 3.02. Almost any intermediate value can be achieved by proper choice of alkyl or combination thereof. It has been established that the compounds show the same general behavior in solution, and they are monomeric non-conducting molecular species. Pressure dependent magnetic studies show a tendency toward the spin paired state with increased pressure. The complete studies on spin equilibrium can be done by using Van Vleck equation. Cobalt 2 plus complexes. The spin state equilibrium has also been observed for D7 configuration. There exists an equilibrium between a doublet and quartet state of the complex. Bis 2,6 pyridine dialdehyde hydrazone cobalt 2 iodide, which has a mu effective is equals to 3.04 Bohr magneton at 300 Kelvin. The temperature dependence studies on the magnetic susceptibility show that the magnetic moment for the complex varies from 1.9 Bohr magneton at 80 Kelvin to 3.7 Bohr magneton at 337 Kelvin. A simple thermodynamic treatment shows the absence of spin orbit coupling and verifies the existence of the equilibrium between spin free and spin paired species.
In this module, we discussed that anomalous magnetic moment is the magnetic moment for a metal ion having a value which falls outside the range of values predicted from considerations of the spin and orbital angular momentum in ligand fields. The meaning of anomalous was explained by taking some examples including octahedral complexes of nickel 2 plus, iron 2 plus and cobalt 2 plus ions, some tetrahedral complexes and also with square planar complexes. The factor which can account for the anomalous magnetic moments of different metal complexes are: first, equilibrium between two spin states; 2. Magnetically non-equivalent sites in the unit cell; 3rd. Solute-solvent interaction; 4th. Solute-solute interaction; and 5. Configurational equilibrium. The equilibrium between two spin states for some nickel 2 plus, iron 2 plus, iron 3 plus and cobalt 2 plus complexes.